Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Hey, Houston, have you ever been on one of those merry-go-rounds? They go around and around and around, and you start feeling loopy? Today we're going to talk about something called circular motion. Now this is a unit on gravity and circular motion. We're going to talk about planets and all this kind of stuff. We already briefly chatted about this. But we're going to talk about how things move in a circle. Now imagine that you're doing this. I've got a string and a weight, and I'm going to spin it. Woo! This is circular motion. So clearly something's going on as I'm spinning the rope with the weight at the end. So what is actually happening in this is we need to define a term, and the term is called centripetal acceleration. So this is this. I'll say it this way: center-directed acceleration. It's accelerating towards the center, right? So something that's accelerating directed towards the center, okay? And here's the weird thing. If I'm spinning the top, here's the thing. If I'm spinning the ball around, what's really going on there is if the ball is moving at a constant speed, we've learned before, constant speed, there is no acceleration. But that's not completely what we've said in the past. What we've said is that acceleration is if you can change the direction or the magnitude. But in this case, since you're moving in a circle, you're changing the direction constantly. So when you're in the circle, right, it is accelerating always, if you will, downward, falling towards the center. But in a moment, it's here, and that's at a different direction. And a few moments later, it's here. So since the direction is constantly changing, in circular motion, the object is constantly accelerating because it's changing the direction of its movement. So let's draw a force diagram looking down on top of the person spinning the ball, if you will. So it's in the packet if you're familiar. So at any given point, so let's say at this point, what's going on? Well, we've got two forces. We've got a force outward and a force inward, because forces have to balance, right? Now, we're not going to assume there's any gravity. There's actually gravity going into the board, if you will. And we've also got something else going on here. Let's just draw that for a second. If it's accelerating constantly downward, right, then that means that there is a force downward. We're going to call that the Fcp, the centripetal force. And then the force that's being opposed is the force, we'll say the reaction force, and essentially this is the tension in the string that we just saw. So we have these two forces. And so you've got forces, also acceleration. We've seen these terms before. I'm going to kind of get a little bit mathematically for you. Mathematically, let's talk about the centripetal acceleration, and then we're going to connect it to force, like force equals ma, because it turns out when you do this whole ball game that the acceleration, the centripetal, so we'll say ACP, the acceleration centripetal, is a function of the velocity that it's moving. That's this. We don't draw that, put that in there. This is the velocity of the ball. If it's moving at a constant velocity, which is actually a changing velocity, because this is really the vector, because this changes in the moments over here, it's moving in this direction, right? V squared over r. So the radius matters, and this is called the centripetal acceleration. Which leads us to, as I said, we have a force. We have the centripetal force, Fcp, is equal to MACP. We know what ACP is, so we can say this is equal to mv squared over r. And you don't think it's like half mv squared. It's not related to like energy. I mean, there's relationships, I guess. But this, if I know, this would be the centripetal force versus this is the centripetal acceleration. Make sense? So one last question I think it's important to note. When you're spinning the ball around your head, and if the string were to break right here, what direction would the ball go? Would it go straight out this way? Would it go this way? What direction would it go? Well, Remember Newton's laws. He says that once an object is in motion, it's going to stay in motion. And if it's moving in one direction, it's going to stay in that direction. So if you're playing slingshot, like you're David in the Lion's Den, not David, David in the Goliath, right? And you got your one stone and you're swinging it around. When do you release the stone? Not when the stone, if Goliath is here, you'll miss if you release it here. You actually want to release it here because it's going to take off, if you will, tangent to the circle. So let's say if I release it here, it's going to come tangent to the circle and come straight down. If I release it here, it's going to come in this direction. All right. So circular motion. This is the kind of the explanation. Next up, let's talk about the mathy part. So example number 1, the 1,200 kilogram car rounds the corner with a radius of 45 meters, etc., etc. What is the centripetal acceleration of the car? Well, we're just going to plug our equation. ACP equals v squared over r, right? And our velocity is 12 meters per second. So we're going to square that. Divide by 45. Comes out to 3.2 meters per second squared. That's it. Not an easy problem. You just plug in an equation. Second question, what's the force? So the force is equal to ma equals the mass. The mass of the car was 45 meters. And the centripetal acceleration was 3.2. And that comes out to 3,800 newtons. And I think this next question, what's the minimum coefficient of static friction to hold that car on the corner? Now remember friction, the force of friction is equal to the force normal times mu, the coefficient of static friction. So we know that the force of friction that you need to have, you must have at least this much or it's not going to hold. So this is actually going to be the force of friction, 3,800. And it's equal to the normal force. Now normal force is the force perpendicular. So if we've got our car right here, right? His normal force is, the normal force is this is the normal force, but it's to the plane of motion. So this is actually going to be his F equals mg, because there is no like angle thing going on. And if you do this, and I'm going to just approximate it, his mass is 40 or 1,200. So I want 1,200. This is F equals ma equals 1,200 times 9.8. When I get that out, I get 11,760 newtons. So that's this number, 11,760 times mu. You divide both sides, right, by 1160 or 11,760, and the mu equals to be 0.33. So if you don't have a coefficient of 0.33, a car slips. You could have 0.5, but not less than 0.3. And this actually explains, if you think about why a car goes off the road in an ice storm, the coefficient of friction drops, and if it drops below 0.33 in this instance, and that car is moving at whatever speed, 12 meters per second, it's going to slip off the road. And so it's important this has to do with the function of the tires and the road and the surface and all that stuff. So example number 1. Example 2, I think this is a pretty cool question, is that you've got a car, it's traveling, and there's a dip, if you will, in the road, and the car is at the bottom of the road. And what's going to happen to the weight when you get to the bottom? So, and the diameter, or probably the radius of this circle is 65 meters. Drawn picture, it's a good thing to do, right? And so he's moving at a constant speed. So let's think about that. What is his weight? Normally his weight, right, the weight of the car is equal to mg, right? F equals mg. So let's actually calculate this. So he's just sitting, when he's sitting up here, what's his weight? Without the whole centripetal thing. So this is going to be equal to 81, the mass of the person, times 9.8, right? And that comes out to be 794 newtons. Got it? So that's the weight of the guy, normal, right? But as he goes down, he's going to have some additional weight, or maybe some less weight. Let's think about that. As he goes down, is he going to feel heavier when he's at the bottom of the curve? Now think about this. You know the answer to this question because you've been on a roller coaster. On a roller coaster, when you're at the bottom, do you feel heavier or lighter? Think it? That's right, heavier. At the top, you feel lighter. So we're going to add his centripetal force. So we're going to use the centripetal force equation. Remember that was from previous, we talked about that. Centripetal force is equal to m times the ACP, which equals m times, I always forget this equation myself, v squared over r. So now we plug that in. His m is still 81. Now his velocity is, what did they say in the problem? 18 meters a second over, and that's squared, divided by, the radius was 65 meters. When you get all that number, you come out with 403 newtons. So what's the answer going to be? At the bottom, that's actually quite a bit. He normally weighs 794 newtons. He's going to add, so we add these two numbers, 794, add them together, and we come up with 1198 newtons, about 1200 newtons is his mass going to be. And you've experienced this. This is actually the principle of a roller coaster, is you're going to feel heavier at the bottom of the arc. It gets a little weird when we have upside down because we've got gravity pushing down, but in this case we just have gravity down. And we can calculate the weight of this. Houston, we don't have a problem. Let's keep on learning this cool stuff because I know you can do it. Circular motion, not so hard because you're awesome.